Hello. So up to this point in the semester, we've been talking about models that assume that the responses are all independent of one another. And mostly we've been talking about how they're independent and all have the same variance. In the last couple of lectures, we looked at cases where we allowed the variance of the different observations to depend on a covariate, for example, and that led to we needed maximum likelihood estimation for that, and that for specific example we used something called weighted least squares. Now we want to generalize things a bit and allow for models that allow the responses to be dependent on one another. So we're going to allow covariance between some responses. So let's look at some specific examples. Our most general model so far is this y is normal, multivariate normal. When we specify multivariate normal, you have the mean vector and the covariance matrix. We've assumed that the mean vector is linear as a function of some covariates, which are contained in the design matrix X. And then there's a covariance matrix sigma sub theta. So B is going to be the parameters that tell us about the mean, and theta are going to be the parameters that tell us about the covariances. So these two parameters and theta we're thinking of as a vector with m components. All right, so some specific examples. The first one, we're going to start with a simple model that's often just called a random effects model, but we'll look at lots of different types of random effects models. So in this model, we have a factor with capital J levels. We're going to indicate that factor with the notation lowercase j of I. That tells us which level the ith observation belongs to. And here's the model. The model is capital YI is B0 plus B, capital B sub j of I plus epsilon I. Now we assume that the B0 is the same assumption we've had before. This is just a number. It's a non-random thing, but we don't know what it is. But we make a little bit different assumption on this capital B sub j of I. The assumption is the following, that this collection of random variables, uppercase B1 up to uppercase B sub j, are independent and all of the same distribution, and that distribution is normal, mean 0, variance sigma 1 squared. And then we have the same assumption as usual on the epsilons. These are independent, normal, 0, sigma sub 2 squared. So we have to be a little bit careful about the notation here. We don't want to assume that this collection of random variables, these effects associated with the levels of the factor, have the same variance as the error terms. So we use a different symbol, sigma 1 versus sigma 2, for the standard deviations of those two distributions. Now, if you take the collection of responses, y, and put them in a vector, y1 up to yn, this has a multivariate normal distribution. So in order to fully specify that multivariate normal distribution, we need to figure out what the expected value vector and the covariance matrix is. So if we look back up to our general example, turns out that this model here that we've just specified falls into this category of models, multivariate normal, mean XB, covariance sigma theta. So what we're going to do next is figure out what X and B are and what sigma sub theta is. All right, let's start with the expected value. If we just take this model formula, to get this expected value vector, we have to compute the expected value of each individual y sub I. So let's do that. Expected value of y sub I equals this expression. Here I'm just plugging in the right-hand side of this equation. Now if you look at what's in here, we have a non-random term plus two random terms. So whenever you have that, you can pull out the non-random term, so b sub 0, and then do the expected value of each of the individual random terms. So this becomes b sub 0 plus expected value capital B sub j of I, remember this is a random variable, plus expected value of epsilon I. Now by assumption, these b sub j of i's, these have expected value 0, shown here in this normal distribution. And as usual, the expected value of the epsilon terms are 0 as well. So expected value yi just becomes b sub 0. Now, that answer b sub 0 did not depend on I. So that means that each observation, y sub I, has the same expected value, b sub 0, and we can represent the entire vector of expected values as b sub 0 times the 1 vector, or if you want to write it in exactly the same form as up here, you would write 1 times b sub 0, which is the same thing. Now the covariances is usually a little bit more complicated calculation, but let's go through it step by step. So what we need to compute is the covariance between every pair of observations. So here I'm just going to pick an arbitrary pair y sub I and y sub k. Now the covariance, using the definition of the covariance, you would take the expected value of the product of y sub I minus its expected value and y sub k minus its expected value. So y sub I is b0 plus b sub ji plus epsilon I. Its expected value we just calculated is b sub 0. So this is yi minus its expected value. And this here is yk, b sub 0 plus bjk plus epsilon k minus its expected value, b sub 0. Now, a useful thing happens here. The b sub 0s will cancel. So you're left with this expression here. And then we just do the FOIL operation. So it's a expected value of a product of two terms, each of which has two individual terms. So we get 4 terms here. So this is expected value bji bjk, expected value bji epsilon k, expected value epsilon I bjk, expected value epsilon I epsilon k. So we'll just take each of these 4 terms one at a time. Now if we look at the, let's try to get this all on the same page here. So we're at the bottom here. So the way I've organized this is this first term corresponds to this, second term corresponds to this, third term is this, and the fourth term is this. So let's go through them one at a time. Expected value b sub j of I times b sub j of k. Now there's 2 different scenarios that could happen. You could have that the ith observation and the kth observation have the same level of the factor, or not. If they have the same level of the factor, so for example, if the level of the ith observation is 1 and the level of the kth observation is also 1, this becomes expected value b1 times b1, which is the same thing as expected value of b1 squared. Now, if that's true, by this assumption up here, that's going to be the variance, sigma 1 squared. Now, on the other hand, so that's where you would get a sigma 1 squared here. On the other hand, if the ith observation and the kth observation are not from the same level, suppose this is b sub 1 times b sub 2, well, we've assumed that they're independent. So then this would become expected value b1 times b2 is expected value b1 times expected value b2. Both of those things are 0, so you get a 0 here. So there's 2 possibilities. Either the ith observation and the kth observation have the same level of the factor or not. And in those 2 cases, you get 2 different answers. Now, we've assumed that the b sub j's are independent of the epsilon I. So this term is 0 and this term is 0. And then the last term is expected value epsilon I, epsilon k. Now, this is going to be 0 if k is not equal to I, if they're different observations. But it's equal to sigma squared if k equals I. In that case, you would get expected value epsilon I squared. And by assumption, that number is sigma 2 squared. So let's put all this together. There are 3 possibilities. The first one is if I equals k, namely if it's the same observation yi and yi, this implies that j of I equals j of k. So if they're the same observation, they must necessarily have the same level of the factor. In that case, we get a sigma 1 squared here, ignore the zeros, plus sigma 2 squared. So in that case, we get this thing. If they're different observations, but they have the same level of the factor, which is entirely possible, you get sigma 1 squared, 0, 0, but this term is 0. So you get a sigma 1 squared here. If they have different levels of the factor, well, then they're necessarily not the same observation, because if they were the same observation, they would have the same level of the factor, and then both of these terms are 0. So in that case, if they have different levels of the factor, their covariance is 0. So there's these three possibilities. Same observation, you get sigma 1 squared plus sigma 2 squared. Different observation, but same level of the factor, you get sigma 1 squared. And then different levels of the factor, you get 0. So putting that all together, you get this is the covariance between an arbitrary pair of observations, yi, yk. Now you could use this to given a data set to fill in what the full covariance matrix is. And that's actually what I'm going to ask you to do on the exercises for this week for different types of models. One additional point is that here the parameters in the covariance matrix, sigma sub theta, remember this will depend on some parameters. The parameters here are simply sigma 1 squared and sigma 2 squared. Those are the two parameters that define what all the covariances are. Now, if you look back up to the random effects model, and I've just repeated it here, this model looks very similar to the one-factor model that we studied several weeks ago. And when you go to fit the random effects model versus the one-factor model, you often get very similar results. Namely, you often get similar estimates for b sub 0, for example. And often similar estimates for the variance of the error. But they are different models. They specify different assumptions about the effects. So the effects due to the factor. So let's review what that is. In the one-factor model, we have this model. The difference here is that these b sub j of i's are not normal random variables. The assumption here is that this collection of parameters are just numbers. What I mean by that is they're numbers, but we place no assumptions on what the distribution of the collection of these numbers are. Now that's different from the random effects model. So this is the random effects model. In the random effects model, we make the same assumption about the errors, and this is a typo here. This should say sigma sub 2 versus sigma sub 1. These are two different variances here. The difference here is that this b sub 1 sub b sub j follow a normal distribution, whereas up here in the one-factor model, there's no assumption placed on the distribution of these numbers. Okay, now we fixed the typo here. This should be sigma 1 squared, sigma 2 squared. So the variance of the effects is different, potentially different from the variance of the errors. Okay, now the way I want you to think about this random effects model is the following. The random effects model is the same as the one-factor model, aside from the fact that it places a stricter assumption on the effects. Namely, it says that they follow a normal distribution, as opposed to the one-factor model, which places no assumption on the distribution of the collection of the effects. So, when should you use a random effects model versus the one-factor model, the non-random effects model? Like I said, they often give similar results, but they are different models, and they will give slightly different results. Now, for this question, you will probably hear a lot of folklore about this question. So you will hear things like, you should use the random effects model when the effects are random, or you should use the random effects model when the effects come from a population, or you should use the random effects model when you don't care about the individual values of the effects. So I'm here to tell you that this is folklore. A lot of people will say these things, but I think there's really no good justification for using these as reasons to fit a random effects model. So let's just think about them for a second. For this one, you should use the random effects model when the effects are random. Well, how do you know that? The effects always come from some population, which brings me to the second point. You should use the random effects model when they come from a population. Well, they're a collection of effects, so they're always going to come from some population. The difference with this specific random effects model we've written down is that population follows a normal distribution. The third one you often hear is, and there are others, it's not just these three, when you don't care about the values of the effects. So that's also not true. You'll see when you use the LMER function, you can actually get estimates for the effects, even though if it's not printed out in the summary table. So I think these are not good justifications. The way I'd like you to think about this is, since the random effects model places an additional assumption on the collection of the effects, you should treat that assumption just like you treat any other assumption you make when you specify a statistical model. So let's review how that works. Well, should you make an assumption? Well, you should make that assumption when you think it's close to correct. For this case, if you think the collection of effects follows something close to a normal distribution. And when you think that assumption will help you somehow in doing the analysis, or it helps you answer the question that you're interested in. That could also be, you think maybe the analysis would run faster if speed is an issue. So sometimes these random effects models are faster to fit when you have a lot of effects. So let's look at an example to show you what I mean when we talk about you think the assumption will help the analysis. So the example here, the factor is patient, and in this study, each patient is going to take 3 systolic blood pressure measurements. Before we get into this, one reason why you would use a random effects model is when you have something called repeated measures. So this is an example of a repeated measure study, namely that there's individuals in the studies are patient and they take more than one measurement per patient. So here's the model, same model we wrote down before, same assumptions we had before. This is a non-random parameter. The collection of these effects follow a normal distribution with unknown variance sigma 1 squared, and the distribution of the errors is normal with some other variance, sigma 2 squared. The goal of this analysis is we want to estimate the distribution of blood pressure for a new patient who's not in our sample. So already we can see that a normal random effects model is going to be potentially helpful here, because the question here is talking about the distribution of blood pressure, and this model places an assumption on what that distribution looks like. Okay, now if we think back to the fixed effects model, that model is going to offer us no help to answering this question. So if we think of a sample with capital J patients, and we get the 3 measurements from each patient, we can get this collection of effects. So the estimated expected blood pressure for patient J is going to be B0 plus B lowercase j. So the collection of these effects is B0 plus B0 hat plus B1 hat up to B0 hat plus B sub j hat. Now this collection of effects, since we've made no assumption about what these distribution these effects come from, this will say nothing about the effect for the new patient, patient capital J plus 1. However, in the random effects model, the effect for the new patient, patient capital J plus 1, is going to be B0 plus capital B sub J plus 1. If we assume that this patient, J plus 1, comes from the same population as the patient in our study, then we are assuming that it follows the same distribution as this collection of effects, B sub 0 plus capital B sub 1, up to B sub 0 plus capital B sub capital J. And when we fit this random effects model, we get an estimate for B sub 0, and we get an estimate for the variance of these random effects, namely sigma 1 hat squared. So for this new patient, we can estimate the distribution of the blood pressure for the new patient as normal, with estimate the mean of our from our sample and the estimated variance of the effects from our sample. So this model will give us an estimate for what distribution we expect the new patient's blood pressure to come from. Now, some caveats. The word random is often used to describe these models. We call them random effects models. But more specifically, the models we've written down are normal random effects model. So it's possible that you have a collection of blood pressures that come from a distribution, but that distribution doesn't happen to resemble a normal distribution. So, for example, if your population has a few outliers with very high blood pressure relative to the rest of the population, then the normal assumption probably won't be good for that population. So if the effects are not normal, assuming normal can hurt you. Now, there are other random effects models where you place a different assumption on the collection of effects. You might assume it follows a gamma distribution or t distribution or something else. But that would be a topic for a more advanced course. Now, that one factor model that we've just studied in detail is just one of many random effects models. So we looked at its distribution and the assumptions it makes. We worked out its expected value, and we worked out its covariance matrix as a function of the parameters and the factor levels. You can get much more complicated with random effects models, and what we're going to do for the rest of the lecture is to look at some of the commonly used random effects models that specify different assumptions on the dependence structure in the data. So here's one. You might expect the next most complicated one you could do is a two-factor random effects models. So as before, we have a factor indicated by j of I, and the levels of this first factor are 1 up to capital J. And then we have a second factor indicated by k of I, indicated by levels 1 up to capital K. And here is the two-factor random effects model. Basically, it's going to be exactly the same as the one-factor model, but we're going to add additional term for the second factor. The assumptions here are the collection of these effects, B1 up to Bj, are independent normal, mean 0 variance sigma 1 squared. The collection of the effects for factor 2, C1 up to C capital K, are independent normal, mean 0 with a different variance, sigma 2 squared. And then, of course, we have the error terms, epsilon 1 up to epsilon n. This collection of effects is independent, normal, mean 0, with another different variance, sigma 3 squared. So we're just adding an additional term to the one-factor random effects model for this second factor. All right, oftentimes we see what people call nested random effects models. So we're going to look at a specific example here to show you what I mean by that. So here's a data set on student achievement. So each row in the data set is a specific student, and they're labeled with I. So I equals 1, I equals 2, I equals 3. These students come from different schools. So we've just written out the first 10 observations. And in this data set, the first 5 come from school 1, and the second 5 come from school 2. And then within each school, we can have different classrooms. So the first 3 observations come from the first classroom from school 1. Observations 4 and 5 come from the second classroom in school 1. And then observations 6 and 7 come from the first classroom in school 2. And then the rest come from the second classroom in school 2. So we're labeling the school with J of I and the classroom within the school with K of I. And then there's some outcome measure, say a score on a test, that will label Y sub I. So let's think about applying this two-factor model to this data set and think about whether this makes sense or not. So the two-factor model is the following. Y sub I equals B sub 0 plus B sub J of I plus C sub K of I plus epsilon I. And then I've just rewritten out the assumptions placed on these 3 terms. So I'm going to contend that this model actually does not make sense for modeling this data set. So what I'd like you to do is to pause the video and think for at least a minute. I'm telling you that this does not make sense, and I want you to think about a justification for why this is not a good model for this data set. So pause it now. All right, so why does this not make sense? So hopefully you did a little thinking on this and came up with a conclusion similar to what I'm going to just talk about. So the reason this doesn't make sense is that classroom 1 in school 1 is different than classroom 1 in school 2. So these are two totally separate schools. Even though we've given this classroom the label 1, it's not the same classroom as the classroom we've labeled 1 in school 2. It's different school, different teacher, different students, so on and so forth. So we really need to do something. So this model doesn't make sense because we're saying that the first classroom in school 1 shares an effect with the first classroom in school 2. So whatever is happening in this classroom in terms of student achievement is applied to this different classroom in school 2 because they have the same label, K of I, for the classroom. Now that doesn't make sense because they're totally different classrooms. Now this model is better. Y sub I equals B sub 0 plus capital B sub J I plus a different term, capital C, indexed by both school and classroom, plus the error term. Now this one makes more sense because this would differentiate C11, so classroom 1 in school 1, from C21, which is classroom 1 from school 2. Those would get rightly different effects. Now, the reason we're calling this a nested random effects model is because classrooms are quote-unquote nested within school. But I think this is really just making things way too complicated. So here we write classroom 1 in school 1 is different from classroom 1 in school 2. This is just making things way too complicated. This is simply a labeling problem. The fact that, and it's a labeling problem because we've given the same label 1 to classroom, the first classroom in school 1, and label 1 to the first classroom in school 2, even though they're different classrooms. If we had given each classroom a unique identifier, suppose we had labeled these 1, 2, 3, 4, then we could use this model with no problems because so the first observation would get B0 plus B1 plus C1, and then this sixth observation would get B0 plus B2 plus C4, and this classroom would get C4, this classroom would get C1. They rightly would not share an effect, and this model would be perfectly fine. So that's what I write here. The first model would be okay. So to summarize this model, what I want you to take from this is that this idea of nested random effects model, classrooms nested within schools, I think this kind of makes things more complicated than it needs to be. If you simply give each individual classroom a unique label, like for example, if you label this 1_1 for school 1, classroom 1, 1_2 for school 1, classroom 2, and then this one 2_1 for school 2, classroom 1, so on and so forth, then you could just fit this two-factor model. You would get different identifiers for each of the individual classrooms, and everything would be fine. So the way I like to fit these models, where I've given a data set that looks like this, is I'll create a new column that's like school_classroom and use that variable as the factor to indicate the factor. All right, so the next model I want to talk about is the random intercepts and slopes model. So again, the response is lowercase y sub I. In this case, we'll just have one factor, but of course you can add multiple factors to this if you have them and want to model them. That factor will notate as j of I. And then in this model, we're going to have a numeric covariate given by x of I. So here's the model. Capital Y is B0 plus B1xi. This is looking like things we've seen before. But now we add to that C sub j of I plus D sub j of I xi plus epsilon I. And the assumptions we make are the following. C1 up to Cj are independent normals. D1 up to Dj are also independent normals with a different variance. And then the errors are, again, normal with a also different variance. So these kind of models are useful when you have repeated measurements for the jth subject at different values of the numeric covariate. So if we go back to this systolic blood pressure example, suppose these three systolic blood pressure measurements were taken at morning, noon, and evening, and in addition to wanting to know about the distribution of each patient's blood pressure values, you also wanted to know how those blood pressure values varied throughout the day. Then you could fit this random intercepts and slopes models where xi is time of day. Okay, so what are the interpretations of these coefficients? So B0 is the expected intercept. How do we get that? So if we plug in xi equals 0, we're going to get yi is B0 plus 0 plus C sub j of I plus 0 plus epsilon. So B0 is the expected value of the response when the covariate is 0, because this term has expected value 0 and this term also has expected value 0. So among the population of patients or subjects, this is the expected intercept. This B1 is the expected slope. So if you look at this here, if you take, so the slope is going to be, for each patient, is going to be B1 plus D sub j of I, if you collect terms that multiply xi. So the patient j's slope is B1 plus D sub j. And if you take the expected value of this, you get B sub 1 because this has mean 0. And then the intercept for subject j is going to be B0 plus C sub j. So we're thinking of this as each individual subject has its own line as a function of x sub I. And then the slopes and intercepts for those lines follow normal distributions, where the expected value of the intercepts is B sub 0, and the expected value of the slopes is B sub 1. But within each individual subject, you'll get a slightly different slope and intercept depending on what the variances of these things are. And in the exercises this week, we're going to have you take one of these random intercepts and slopes models and plot the distribution of intercepts and slopes so that you can get a feel for what these models look like and what they're assuming about the data. All right. Now, this is just a few examples of different random effects models, but you can take any model we've studied this semester and turn it into a random effects model by placing a normal assumption on the coefficients. Usually, we're going to consider random effects models when we have a factor in the model with several levels. And when we want to make the assumption that the coefficient corresponding to the level of the factor follows a normal distribution. This last one we just studied is a perfect example of that. Basically, we want to assume that the intercepts for a sample of j subjects follow a normal distribution centered at B sub 0 and with variance sigma 1 squared. And when we want the collection of slopes to also follow a normal distribution centered at B sub 1 with variance sigma 2 squared. So basically, when you have a factor in the model and you want the effect of that factor to follow some normal distribution, then you can turn it into a random effects model. And basically, your imagination is the limit here. You can take different types of random effects model and combine them to get more complicated random effects models, and you can estimate them. But the thing to remember is to always think carefully about the assumptions you're imposing. And this doesn't just apply to random effects models. This applies to everything you do in statistics. Like I said in the very first lecture, statistics is all about deciding what you want to assume to be true, namely your assumptions, and what you want to be estimated from the data, which usually is parameters that specify distributions. All right, so that's basically theoretically what the models are. What are the mathematical equations? What are the properties of those models? How do we estimate them when we have real data? So in R, there's a package called LME4, and within that package, there's a function called LMER that is, I think, the most common method used to estimate random effects models in R. Now, there are other packages as well. There's the other one that I think is not also popular, but probably not quite as popular as LME4. It's called NLME. There's another package that's called Regress that I think someone is working on now to kind of update to make more modern. So keep an eye on that one as well. Okay, but let's just talk about LME4 because I think that's probably the most popular one. So suppose in R you have data vector y, so a length n vector y. Two factors, fact1, fact2. Fact1 will have j levels, fact2 has k levels, and then two numeric vectors, and I'm just calling num1 and num2. So the syntax in R is similar to the LM function, but in this case, we have to tell R which effects we want to assume are random effects, and there's a specific syntax for that. So here it is. So just like before, we would put y on the left side of a tilde. If we want to fit the one-factor model, we're going to need the intercept, so this gives you the B0 term. And then to indicate a random effect, you put inside of quotations the type of effect you're doing. So in the one-factor model, basically it's an intercept. So basically it's not multiplied by anything. The B sub j is not multiplied by anything. So you put a 1 here, and then this pipe symbol, which is usually beneath the backspace key on your keyboard, and you have to use shift to get it. And then the name of the factor you're using. So this would fit the one-factor model, the very first model we looked at. Now, you can also add fixed effects. So for example, sometimes you'll want to make one of the factors non-random, just a regular fixed effect, and one of the factors random. So if you do this, that will accomplish that. Here you'll get you're placing no assumption on the collection of effects for factor 1, and you're placing a random effect on the collection of effects for factor 2. And this is a good example of kind of using your creativity to combine different types of models. So this is how you would do that. If you want, you can also add numeric covariates. So if you wanted a non-random effect for the first numeric covariate, so this will do intercept plus B1 times num1. But you also want to have random intercepts according to factor 1. This will give you that. Basically, if we look back at this model, that would fit the model that excludes this term. So if you want to have the same slope for every level of the factor, namely B1, but you want the intercepts to follow a normal distribution, you would fit the model that excludes this term here. So you'd get B0 plus B1 xi plus C sub j of I plus epsilon I. And this is the syntax for fitting that model in LMER. Now, if you want the random intercepts and random slopes, the syntax for that is basically this thing here. So you're assuming that both the intercept and slope with respect to the first factor intercept and slope with respect to the first numeric variable varies by factor, and you want them to follow a normal distribution. This is the syntax here. Now that's the code. R kind of just does it for you. What is LMER doing in the background? Well, you can tell LMER whether you want to use maximum likelihood estimation, which we studied in the previous module, or residual maximum likelihood estimation, which we also studied. By default, it does REML, residual maximum likelihood. So it kind of does everything for you, but what it's doing is it's forming covariance matrices, and it's optimizing the likelihood function. It does all that for you. So your exercises for this week, we're going to ask you to work out what the covariance matrices are for these different types of models. So we did it for the one-factor random effects model. We figured out what the covariance between pairs of observations are. You can do that for any of these models. So if you were to code up LMER or a method for fitting these models by hand, what you would have to do is figure out what the covariance matrix is, and then you'd have to optimize the function as a function of any parameters that go into the covariance matrix. So those exercise for this week is you're just going to work out what those covariance matrices are, which is the first step to writing your own estimation method for random effects models.